Okay, in this video, we're going to actually get into the theory of computing the length of a curve using calculus. Actually, we're going to start with just the idea of summations, and we'll build into the idea of using the integral in a later video. So first of all, you can see I have a nice curve here in blue, and I've connected it between red. I put in points every 2 units along the x-axis. We could connect those points with straight lines. Let me add some straight lines. And you can see if I were to string these points together, the string keeps cutting to the inside of the curve. So if you thought of this as a race, the black lines would be a lesser distance than running the curve. So it's a slightly shorter distance, but not by much. You can imagine if I use more points, I could get the string to be closer to the curve and cut those gaps down. And eventually, with enough points, we could match the length of the curve. So let's look at a section of curve sort of in the middle of this. Let me switch to my pen and we'll go to green. So let's consider this second length. So we'll call these lengths L1, L2, L3, L4, and L5. So the curve is made up of 5 lengths, and we're going to approximate those as straight lines. So if I wanted to know how big L2 is, we'll have a length element. All right, it would have a width to it, so that would be a delta x. We could call that delta x2 if we want it, and it would have a height to it, a delta y. We'll call that delta y2. So hopefully you realize this is a right triangle, and so we could simply use the Pythagorean theorem, and we could say that delta L squared, maybe I should put that in parentheses, the quantity delta L will be squared, is equal to delta x squared plus delta y squared. All right, and while we're doing that for region 2, we could easily have put in triangles, a little bit of geometry. We could put in triangles for all of these. It looks like this triangle actually goes downward a little bit and over. So L4 is almost a horizontal line, but we could put all 5 triangles in. So this is a representative length element. Obviously, if we want to solve for delta L, all we need to do is take the square root of the delta x's squared plus delta y squared. And it's that simple, all right? What we're going to do is then break this down into using calculus in the limit that delta x gets really, really small, but we'll save that for another video. What we want to do next is actually go into MATLAB and program this in so that for any curve we make, we can break it into little segments and tally up the length of those segments and determine approximately what the length of the curve is, just like we did with Riemann sums for areas. The smaller the segments, the closer we can get to the actual length of the curve.